The sun exists on a scale that dwarfs the Earth. The Earth is to the sun as the ball in a ballpoint pen is to a very large grapefruit. The sun is 99.8% of all of the mass in the solar system. So if you take all the mass in all the planets and all of the over 200 moons that go around the planets in our solar system, all of that mass adds up to only 0.9% of all the mass in the solar system. 99.8 of it is in the sun. So the sun exists on an enormous scale. It exists on an enormous scale in size, but it also exists on an enormous scale in terms of energy. You can see a plume of fire and plasma that's ejected from the sun here, and there's a Earth to scale next to it that you can compare. Now this is happening every second, and the sun ejects not just all of these wild fiery particles, but it also ejects waves of electricity that can burst things apart when the waves of electricity hit them. Now, some of those waves of electricity we experience as light, the light of the sun. Other waves of electricity we don't perceive as light, and yet they are there. Some of them go through us, some of them dig deep into us. That's the type of things like ultraviolet light or X-rays or gamma rays that have caused both a lot of damage to things on Earth, but also have caused some creative change. Damage in the sense of DNA, the highly energetic electric waves that radiate from the sun, can break DNA apart. At the same time, it can mutate DNA and so cause sparks of evolution, branches in evolution. But if it weren't for a layer of a very special molecule called ozone, the electric waves radiating off of the sun would be so energetic and so dangerous that they would have destroyed life on land, on Earth. Life would have only had a chance buried deep in the oceans where the electric waves coming off the sun wouldn't be able to reach. The reason why life exists on land is because there are gases in our atmosphere that help protect us from it, and one of the most important is called ozone. At around 25 kilometers above the surface of the Earth, that's around 15 miles. So if you drive 15 miles straight up into the air, you get a layer of ozone. And we've seen ozone before, it's O3. We've been using it as a reagent to do things like ozonolysis of alkenes and alkynes. The layer of ozone that's 15 miles above our heads is only about 3 millimeters thick on average. The width of a penny is around 1 milliliter, so around 3 pennies thick, less than the thickness of an eraser on the end of your pencil. That's a layer of this ozone gas that exists around Earth. Now, it's not spread evenly out. This is an animation of satellite images laid over an animation of the Earth. The light blue here are the thickest parts of ozone. You can see there's at least a shimmer of blue almost everywhere. Although once a year over Antarctica, the ozone almost completely disappears, and the violent electric rays of the sun pierce through onto the land in Antarctica. And if living things were there, and the creatures weren't wearing sunscreen, those violent electric rays would cause mutations in their cells and would burst apart molecules in those cells. It's tempting to dismiss things that we can't see. You can't see ozone, but you could see how dramatic that ozone, that hole in the ozone layer is when you visualize it with different colors. So if you were to see it with colors, that blue there would be the hole in ozone above Antarctica that appears once a year. So how does ozone protect us from those violent rays of the sun? And why is ozone being depleted in those holes like the hole above Antarctica? And in general across Earth, although people are trying to do ozone remediation and increase the amount of ozone in the upper atmosphere. In the lower atmosphere, ozone acts as a greenhouse gas and contributes to global warming, but very high in the atmosphere, it helps protect us from ultraviolet light. So how does it do that? Well, first, ozone is O3. That's how we've seen it before in ozonolysis. And the structure of that is 3 oxygen molecules bonded, or 3 oxygen atoms bonded to each other. The 2 on the end are each radicals, and here I'll draw the unpaired electron in red so that it stands out. So that's ozone. Now when that violet light, the ultraviolet light that gives us a tan, but also would give us like skin cancers. So those bright lamps that people sit under in tanning beds, those lights are ultraviolet lamps. Indeed, it gives them a tan, but it also increases their chances of getting skin cancers and also contributes to premature aging. Ultraviolet light, that violent light that's emitted by the sun, doesn't just break apart DNA, it can also break apart the bonds in the protein collagen that keeps your skin firm and keeps you looking young. Collagen is the most prevalent protein in your body. It's around 60% of all the proteins in your body, and it sort of acts like elastic that keeps your skin firm. When it's exposed to ultraviolet light, the ultraviolet light can break it apart and break it down, and your skin becomes less firm. That's why spending time in direct sunlight without wearing sunscreen can lead to premature aging. So how does ozone protect us from that dangerous ultraviolet light? Well, when the ultraviolet light from the sun hits ozone, a similar thing happens as when the ultraviolet light, that H nu, right, we've been representing this as H nu up until now, the same thing happens as when that H nu ultraviolet light hits halogen molecules, or peroxides in general. You have homolytic cleavage. One electron in the bond goes on one oxygen, the other electron in the bond goes on the other, and ozone breaks apart into 2 molecules. One is what we normally think of as oxygen, molecular oxygen, O2, and the other one is just one oxygen atom with 2 radicals on it. So these are very reactive species. But up there, 15 miles above our heads, once these ozone molecules break apart, they just couple back together, if all goes well. And so you recreate the original ozone that you have. It might appear like nothing changed from the beginning of this reaction to the end. You start with ozone and you end with ozone. But something really important did change. In the beginning, you had dangerous ultraviolet light, and at the end, you don't. It gets absorbed, it breaks that bond, and then it's gone. It's now being expressed as heat. It's being expressed as the vibration of molecules. That random motion of molecules is heat. And so it's not ultraviolet light anymore. It's trapped in the behavior of these molecules, and then as these snap back together and vibrate more, it expresses this ultraviolet light. And the ultraviolet light does not get past this ozone. So if we are on Earth down here, the ultraviolet light does not reach us in this process. And that's how that 3 millimeter layer of ozone in the atmosphere helps protect us from the ultraviolet light. It absorbs it, becomes 2 radicals that snap back together, and that turns the ultraviolet light into heat and prevents it from reaching our cells and breaking the bonds in our bodies molecules apart. Now, we saw how the ozone layer is being depleted in certain places, and in general across the world at around a rate of around 6% per year, although people are trying to remediate that and increase the levels of ozone in the upper atmosphere. And in some places, it's almost non-existent, as in the ozone hole above Antarctica that appears once a year. So what's the cause of that? The cause of that are molecules that humans have released into the atmosphere called Freons, or chlorofluorocarbons. So you see CFC here. There are different types of these, but the CFC is standing for chlorofluorocarbons. They're also called Freons. These are carbon molecules that have both chlorine and fluorine on them. So chlorofluorocarbons. And These molecules were used as propellants and refrigerants. So like in old refrigerators, it was a gas that helped to keep the coolness, to produce the coolness of a refrigerator, or in air conditioning in old cars, it was used to create colder air. When the refrigerators of the cars were thrown away, or the containers that these freons were in broke open on the population level, and the freons were released into the atmosphere. When they were released into the atmosphere, and I'll copy this freon, this specific freon down here. When they were released into the atmosphere, you can see what would happen if the ultraviolet light that normally hits ozone hit these freons instead. What happens when ultraviolet light hits a bond that has a halogen? When H nu hits a bond that has a halogen, it breaks it open with homolytic cleavage. One electron goes on the chlorine, the other goes on the carbon, and you end up with two radicals. It's like the initiation step in the mechanisms that we've been drawing in this chapter. And so, at that point, you would have two radicals, and here I'll fill in the lone pairs on this one chlorine. You have three lone pairs, and now we'll have one unpaired electron coming from the bond, and otherwise we'll have a radical on the carbon, an unpaired electron on that carbon atom. Now these radicals here can act to disrupt this coupling step that reproduces ozone. If you have a radical in the atmosphere that can compete with this oxygen radical, then instead of recombining with ozone, it can combine with this other radical. They can do a coupling reaction. They each contribute one unpaired electron, and they end up making a new bond to each other. But notice that when that happens, you prevent ozone from being remade. Instead of the oxygen combining back together with the two oxygens, with molecular oxygen to reform ozone, it gets pulled in to this other chlorine. And so there are other reactions that happen. This is still a radical, and there are downstream effects of this. But in terms of, on the test, what you would want to be able to explain is the original process for how ozone breaks apart and comes back together. And so you'd want to draw that process and explain how that prevents ultraviolet light from getting through the ozone layer. Then you would want to show how this chlorofluorocarbon, this freon, would also break apart homolytically when exposed to ultraviolet light, and how the radicals that are made in that can combine with the oxygen to prevent the reformation of the ozone. There are other reactions here, and if you're interested, you can come to my office. I would love to go through the other reactions that happen here, but I don't want to overburden you with the further details of this reaction. What I want you to understand is why ozone is environmentally important, how it absorbs this dangerous ultraviolet light, those electric waves, very energetic electric waves emitted by the sun, and protects the life on land, even permits it to exist on land and not get ripped apart by those electric waves, and how the existence of ozone is threatened by these freons that have been released into the atmosphere. So if you can draw the mechanisms that I've drawn, the curved arrow mechanisms that I've drawn in this video, it's not the complete reaction for how these chlorofluorocarbons behave, but it explains the principle behind how they lower ozone in the atmosphere. And if you can explain what we explained in this video and draw the mechanisms in this video, then that's what I'll be looking for on a test on this question on an exam.